Hello, everyone. My name is Roopa. I work for a NOS distribution company, Cumulus Networks, and all my work is focused on getting new Linux features and then offloading it to switch ASICs. And well, I just want to say NetDev, Canada, and summer has never happened before. So thanks, Jamal. It's been warm and nice this time. How do I get this going? Jamal? Where is that?
This thing, here. Forward.
That's
the green
okay,
and the red.
Great. Okay. So I just want to point out that we have done workshops on switch ASIC offloads before, but we've called it switchdev offload and various other things. And you've seen switchdev referred to in a lot of places during the entire conference right now. But most of that work, initial infrastructure was done for switch ASIC support, and now it's been used by many other subsystems. Today's agenda is, I will just do a quick roundup on all the updates, recent updates. Then we have updates from Mellanox from Matty, who's going to talk about some resource management open issues. And then industry perspectives from Srijit and updates from Barefoot. So Mellanox and Barefoot are the two hardware vendors today. So a quick intro. So switch ASICs are the ASICs that go into switching and routing platforms, which many proprietary vendors, Cisco, Arista, all those sell. And the recent trend with open networking and disaggregated hardware for open networking. Linux has been running on those boxes, and one OS is Cumulus, and Mellanox has a switchdev free open source driver in the upstream kernel. So the difference is what the people or the systems that are using Linux control plane to offload to switch ASICs, they benefit a lot from the Linux ecosystem. And you basically use the kernel tables, routing tables, bridging, ACLs, netfilter, and TC, and you can offload it to these boxes. And the Linux APIs that are used today is one is switchdev infrastructure, netlink API, and also notifiers, netdev notifiers. Every networking subsystem has something called notifiers, which sends out async notifications, just like how netlink is sent to user space. So many of these drivers today, they trap these notifiers and offload to ASIC. Hardware updates, what we're seeing right now is in later part of this year or next year, we see a lot more updates or newer hardware coming up with greater scale for cloud and service providers space. And programmable hardware, you've seen in the past TC workshop, a lot of P4 programmable hardware was talked about. Barefoot is one of them. Something in-band telemetry is also another feature coming up in newer ASICs. I guess Mellanox and Barefoot are the two hardware vendors here. Any questions, you can direct to them. They will be on the stage soon. Resource management updates. So ever since a couple of years at Netdev, we've been talking about resource management, a route add, when not offloaded to hardware, was never reported back to the user, and that's a huge problem. So one thing that happened recently was fib notifiers or fib rule notifiers can actually return an error, a hardware offload error, to the kernel subsystem, routing subsystems, and that error is propagated to user space. And for all throughout the slides, I've actually put references to the patches and whatever man pages and any other presentations that made this happen. So you can see them at the end of the slide deck. And there was another series that shows an example fib resource controller by David Ahern, and that is also referenced here. So that is a good example of how you can, it's a simplistic example, but it shows you how you can, how hardware can propagate its resource limits to the kernel routing subsystem. Bridging updates. I and many other people also have been spending a lot of time in getting the bridge driver for latest data center networking features. So private VLANs, if you saw it on the Netdev list, there was a recent patch for port isolation. Tunneling protocol packets, through bridge ports. For example, when a VXLAN is part of a bridge, how do you tunnel protocol packets through the VXLAN tunnel? That's something that went into. Ethernet VPNs, I have talked about it in previous Netdev conferences, and it's another BGP-based control plane for Ethernet VPNs for VXLAN, extended VXLAN bridging domains. So a few more flags were added, a few more bug fixes went in. This is just context for the whole E-VPN thing. What I'm talking about is a layer 2 gateway, a hardware VTEP running over a switch ASIC, supported by a switch ASIC, which is a Tor switch in this picture. Devlink. If you know Devlink, Devlink is the new, Devlink was introduced along with this to support the SwitchDev effort, and now it's again being used by various other drivers, even in the NIC space. So recent highlight was by Jiri from Mellanox, a port flavors for configuring port flavors via Devlink. So, okay. So this is, and mainly it also provided a helper to actually, that a driver can use to generate switch ports. I've just put some code up there. Self-tests. If you have been following Netdev, a lot of tests have been going in for networking, which is a great thing. It's easier to test your code now for any other breakages. So we have been seeing a lot of tests going in for the SwitchDev and Mellanox SwitchDev driver, which you can, and these tests not only work on offloaded hardware, but also on any networking, any Linux VM or purely on software. So you can find some of the tests in these folders. And we and many others have been working on getting a bunch of networking features into the Linux kernel to offload it via the Netlink API or the SwitchDev API to ASIC, and one of them is the policy-based routing. So in Linux, you do policy-based routing with IP rules, and recently we have shown that you can use the free-range routing suite to implement PBR, basically policy-based routing, which installs IP rules into the kernel, and those can be offloaded to hardware. There is a FRR, free-range routing tutorial today by Donald, who's a maintainer of FRR, later today, if you're interested. So the new update here that went in was all these ASICs, they support 5-tuple match, which was missing in IP rules, and that went in recently. Multicast routing. IPMR received a lot of updates, both from the Mellanox SwitchDev ASIC driver and also from other ways people offload via SwitchDev API or the Netlink API. Again, FRR, free-range routing, is a open routing suite that implements the multicast protocol and uses the kernel IPMR database. Scaling. With new hardware, there are many scaling challenges coming later this year and in the future, near future. And one of the things that has been happening, and this is work in progress, which David Ahern has been working on, is for a faster FIB database, FIB routing database, faster convergence. So we are looking at, when a link goes down, you're looking at like tens and thousands, more than close to 500,000 route updates. So the idea here is to split the routing, today's kernel routing, so prefix and next hop groups. You split the route so that you have next hop groups stored separately and updates, you can update them separately. And that makes it easier on the routing daemons, and that's how you can scale updates to the routing database faster. There is a pointer to the presentation by David Ahern there as well. Similar things are happening in the bridge database. Like I mentioned, the Ethernet VPN case, you have to now scale the bridge forwarding database to thousands of entries. And because you're on a TOR or a spine switch, and your bridge domains are now expanding throughout the data center across racks. So larger bridge domains, larger MAC addresses. So similar things are being thought through. This is something we are working on as well. And VXLAN, as you know, VXLAN has its replication groups that it stores. So even one of the cases we've seen for E-VPN, it needs to update these replication groups at a regular interval, and those updates, in today's model, it's not very scalable. So we'll see similar separation of replication group from the VXLAN MAC entries. Scaling network devices, this is another challenge, and this is mostly under control with lighter net devices, lighter net devices has been talked through in Netdev multiple times. We will hopefully see something there. Lightweight tunnels, another reference there. This is to not use a net device for some of the tunnels. And the bridge driver, for example, when VXLAN is a bridge port, for cases like Ethernet VPNs, you can also use a lightweight tunnel device. Yeah, these last few slides are references which people can refer. That's all I had for roundup on updates. And the next speaker is Maddie from Mellanox.
Hi guys, I'm Mati from Mellanox, switches, mainly focus on switches, and what we're going to talk about today is resource management in the upstream driver. And let's go to the problem statement. So there are a lot of hardware offload that are done in work queue, in the background, in asynchronous mode. The reason for that is that the offload API is called under lock, RCU or such, or spin lock. As a result, we need to configure the hardware in the background, because as a result, we do not know currently that there will be a failure. A failure is going to occur. So resource failure will result on asynchronously, and as a result will trigger some rollback mechanism, or which will kill the offload and actually will kill the switch. Again, we are talking about the switch here, and in the switch case, doing stuff in slow path is not an option. It's really not an option. So if you, as a result of route insertion failure or any other insertion failure, neighbor insertion failure, decide to abort, you just kill your switch and kill all the application that the user is running in the data center. So we want to avoid that. Sorry. So what is the goal? So the goal is that abort mechanism will never be called from the driver itself. The driver should never decide to do abort. It may come from the application. Not sure that I see use case why application of a switch will abort, but again, driver should never do that. We need to provide better visibility to the application to understand what are the resources available. And we need to be able to return a failure or success immediately. So where is the catch? Sounds easy. Let's manage the resource, count 10, 100, 100K, whatever route we have, and return a failure if you have less or more. So for that, I want to give you a short introduction on Spectrum 2 hardware. Again, the idea is not to show off or something like that. It's just to give you some brief of how modern hardware look like. So, and this is not only Spectrum. Other vendor and other hardware look more or less the same. So first I want to give you some brief on how ACL in Spectrum 2 works. So in Spectrum 2, we are not using only hardware TCAM to do ACL or ternary match. We are using some algorithmic algorithm that can do ternary match using SRAMs. So the point here is that we allocate some entry within the SRAM called RP, which is rule pattern. I won't get into the details of the algorithm. It is not interesting. It's just to show you that the idea that is to illustrate that managing resources is not so easy. And those RP are stored in the SRAM. The size of each RP is dependent on the key on the mask, the size of the key and the size of the mask. And there is the algorithm that decides per rule whether this rule can sit on an RP or it cannot sit on an RP. It must sit on the TCAM. This algorithm is a heavy algorithm. It's not something you can run very fast. In addition to that, actions are stored in the SRAM as well, and the size of the actions depend on the number of the action that you have per rule and the type of them as well. Next example is LPM. LPM is, again, it is algorithmic LPM. It is not TCAM-based LPM. And for that, we have different routes, different prefixes, different areas. There is some tree structure, and there is some markers that manage the tree structure. So the number of entries we are inserting to the SRAM as a result of route insertion, it depends on the location of this route in the tree and the size of the prefix. And this is for the route insertion. Let's move to the ECMP itself. So the ECMP, again, the number of elements consumed from the SRAM for ECMP is dependent on the size of the ECMP and the type of it, whether it is resilient, consistent, and so on. And this SRAM, in general, actually holds not only the LPM and table, it holds the ACL, as we discussed before. It holds the LPM, IPv4, IPv6. It holds the ECMP, it holds the FDB, it holds the ILM, and some more. So it is a shared resources. So it is quite complicated to understand or figure out how many resources left out there when you're trying to calculate per rule whether it will be success or failure. And in addition to that, the SRAM itself is a hash table. So even though it is a very efficient hash, it is a very cool cuckoo hash table which reach very high utilization still. It is a hash table. So it is not so simple to build a calculator that will give the application or it is, we cannot expose, the idea is that we cannot expose a number to the application. As a result, the application will be able to calculate whether a route will be a success or failure. We need to do something else in order to provide that ability. And this is what we would like to do, or we think, this is what we think we should do. So the idea is to create some resource manager module. Okay, it's not a module, it's not, and actually it is a nice discussion to figure out whether it can be a generic one or it is part of the driver itself and it is per hardware. I'm not sure how generic it is, but the idea is to build the resource manager in a way that it will be able to return immediately a failure or success. Again, it won't insert the route or the neighbor or the TC entry. It will just return a failure or success, and the insertion itself will happen in the background. But in case in case this module returns a success, it means that we have enough resources for that module, and the idea is to try to predict, like take the worst case scenario. For example, if we take the ACL use case, we will assume that the ACL consume a TCAM resource. In addition to that, it consume n SRAM resource according to the algorithm we are running. Again, we won't run the algorithm, but we know what is the worst case scenario for that. We will consume those amount of credit from the ACL pool, from the SRAM pool. Those credits will be updated afterwards. Oh, this error was, never mind. Afterwards, when actually the driver will insert the entry to the hardware, and then it will know exactly how many SRAM lines was consumed and whether the TCAM entry was consumed or not. So there will be like a credit pools and update from the driver to the resource manager on that credit pool, and in that way we will be able to return success and failure immediately when the application will try to insert a forwarding entry to the hardware. Question? Cool. In terms of better visibility, so the idea is to use the dpipe in order to provide table utilization and table usage. And what is the table size? So it will be up to, because again, we have shared resources. So up to means that assuming you are going to insert a specific entry and only that entry, we can give you the ability to know how many entry you will be able to insert. But again, if you are mix and matching between entries, then it will be very hard for the application to understand how much entries will be available. And the last part are open questions. And the question here is whether we need, so using this mechanism, we will never trigger the abort mechanism, and we will go for every resource insertion to the resource manager before inserting this entry really to the hardware. So as I mentioned, the way that the resource manager will work, or in order to do that, what we need to do is to take the worst case scenario. Meaning that, for example, if we know that our utilization in the hash table, let's take a very simple example. Let's imagine that all the entries that we are programming into the hardware are single line in the SRAM. And in the SRAM, we have 100 line, okay? And the utilization is 90%. Still, it is a hash, so even if we have a very efficient algorithm, it cannot reach 100%. So after 90%, there is a very good probability that a route may fail, that you will receive a route failure due to a binful case. So in that case, what we will do, or what we may do in the resource manager, is actually expose 90% only of the SRAM in the resource manager, and if in case you reach that limit, there will be a failure now. So though for route, it is what you want to do because you cannot guarantee whether the route will be inserted or not. Maybe for other resources, it's better actually to try to configure them, and in order to actually to get more from the hardware. We are not sure that this is very interesting. We are just raising that as a question. A good example for that will be a neighbor or an FDB entry, in which anyway you don't. It is those entry are entry that triggered by the kernel itself, not by the application. So returning a failure for such kind of resource is like We don't know how to do that. So maybe it is better to just to try and configure that and do best effort. Again, by doing that, you may be able to actually utilize the hardware to the best. Another question is what to do when there is a failure. Because of a bug, because of something which is unpredictable. Whether we need to generate a new event saying fatal or whatever. And I guess that this is it. Questions?
So just to throw it out there,
Yep.
one thing that Ido and I have talked about is it passed the checks, it says it's going to upload, but something happens with hardware.
Mm-hmm.
Hang on. David.
I'm not much of a pop star. So what I was saying is one thing that Ido and I have talked about is you've passed the credit checks, you have the highest likelihood of success, but something happens along the way.
Mm-hmm.
And what do you do about that? And one thing to do is to send out an error message to user space saying, I can't take anymore. And then you don't flush the hardware, you just stop making updates. So that gives user space notification to say, something happened, we have an error, I can't do any more route offloads, but I'm not going to flush it. So it's something we've just discussed. I don't think anyone's implemented it, so certainly open to suggestions, ideas, or what have you, but that's,
So-
I guess, the top one.
It is written that this is exactly was the intention of the last bullet, but I'm not sure this is what you want to do because
Well,
as
you
I
don't
see
want
it-
to flush.
No,
So if you
I'm
don't
not
wanna
saying flash. I'm not saying
then
flash. I'm saying, and I agree that there should be an event to the application. The question is, what does that event mean? And I'm saying that in that case, it's a fatal. It's like you configure an MTU and I return a failure for that. What you're going to do with that? It's a bug. It's a driver hardware bug. From that point, you do not know what is going on. So probably the best thing will be to shut down the box.
That's I guess the point.
Yeah, and that's my point is you stop making any updates at all.
Right.
So you flush the route queue backlog, you don't let the routing daemon push any more down, and you just say, I can't do anything else. But you will have time to go back and fix it. That's the intention.
So it's fatal without a side effect is what you're saying.
Right.
Mhm.
Right. So you maintain operation up to the point that the first error happened.
I'm not sure. Again, I'm not sure this is what you want to do. I'm not sure. Again, as I see it, if the hardware has a fatal error, it shouldn't follow traffic. You don't know what is the state of the hardware. You do not know what is the state of the hardware.
But you don't know either that but at the same time, you don't know the hardware is doing things wrongly. Meaning, you should let it work, send a notification, let the user.
No, of course. We're not going to reset the hardware ourselves or kill it. Yeah.
So the
We all-
example that you used, Matti, the MTU failure, or there's a link, take a really extreme example. You have a lot of link errors. Yeah, you can say, or you have actual SRAM failure, right?
Mhm.
Like somebody is not refreshing right or whatever. I totally agree with you. But in this case, if the driver knows that it latched an error on update because of TCAM capacity failure or not, and that's the question. I think the question comes down to is, can we say that it's a capacity failure, not a generic memory error? Because Matty's argument is, if the TCAM is AFU, then forwarding any frame might be just blasting runs all over the network, right? For example.
Sure, and
Yeah.
it could be a million errors.
Right.
You're
So,
just doing a
so
lot. Yeah.
as long as there is a clear indication that this was a capacity failure, I think holding your position makes sense. If you're worried about it being the generic answer to any failure from the driver means hold the tables in its current form, then Matty's concern is correct, right? It's a problem.
So. No. So again, let's go back.
Brought up neighbors. Neighbor table is a weird one, right? And it's not always from the user. You're learning entries.
Yeah.
Not all of them are needed to go in hardware.
Mm-hmm.
And what do you do in that case? Have you guys thought about the neighbor table?
Yeah, of course. So today you're totally so. I was referring to the new model in which we have a resource management which know how to calculate resource. Okay, so if resource manager return a failure, that's a resource failure by definition, and it is valid. So yeah, so nothing happens. So you got a failure, you can do whatever you want to do with it. You may ignore it or decide not to insert more routes. Now, if the resource manager returns a success and the driver returns a failure, from my perspective, it is fatal. It's something unpredictable. Yeah, of course, unless we, again, if we have a, no.
Yeah, I'm saying, I think what David is proposing works for all of those scenarios, right? If the indication from below is it's clearly a capacity failure, then stop everything. Your resource calculator will fail. The next app update will fail. The app will know that there is a problem here and it has to handle, and it will treat it as fatal. And maybe you even have a handshake for the app to come back and say, I've cleared the state, now flush, right? Because that gives an upstream router a chance to clear away and say, okay, I've steered traffic away, now kill your link. But in the case where it's a generic failure, your concerns are 100% valid. You have to kill everything because you don't know what the failure mode is.
Sure, it's really getting after a starting point. You're just going after a start point to gain that knowledge on the different error paths handling, because today there is none. And so you've got to start gaining some knowledge about what are the errors you think you can keep moving on, and what are the errors where you do have to go, I'm done, I'm belly up.
Exactly.
Okay.
Multiple types of failure. There's no single type of failure.
I agree, though. I think we should keep it simple.
Yeah, but the driver
It's like resource error and fatal error. I don't think that you should, like, there are a lot of in between. If there are a lot in between, nothing will happen. Like, too complicated.
should be declared when the driver, which knows how the hardware works, should declare. Fatal should be declared by the driver that the driver itself doesn't know how the system will behave, and then you probably have to shut it down. But
So,
if the driver knows that it failed, but the previous state is still legit, meaning the system is still running correctly,
Yeah.
you shouldn't stop.
We all agree. So there is a resource error which is resource and totally valid. Everything is consistent. There is like configuration errors. You try to do something that I do not know how to do, right? It's valid as well, nothing wrong. And there is something, you try to configure something which I shouldn't fail. You try to add a VLAN to a port, and this is fatal. Kill the system. You have a question on neighbor table?
Sorry, what did you say?
You have a question on neighbor table?
No, dynamically learned neighbors, right?
Dynamic.
But the
FDB,
kernel
like,
is
yeah.
learning, even FTP,
Yeah.
for that matter. Have you guys given any thought on?
Hmm?
Have you guys given any thought on how do you?
So this is actually fall into
That's the open question.
neighbor question, whether this should go to the resource manager and or bypass it. Anyway, in our hardware, so, and as a result, the credit will be updated. So it will be,
Okay.
we can manage it in a way that we, in case you have a neighbor, you have a route that actually you want to configure a route on the same table that was now utilized or by an FDB entry, you have a choice actually to define what will be the behavior, whether we override or not. But currently we are not. Currently there will be a failure.
So this RSM that you're talking about, are you planning to make it a generic resource manager on moving it into the core or keeping it in?
That's a good question.
Yes.
Currently, the logic of that model is totally Mellanox specific. So I'm not sure it should be a generic, but this is like open to discussion. I don't know.
Okay.
Okay.
Any
Thanks.
other questions? Okay, thanks, Maddie.
Thanks.
Next speaker is Shujit Mukherjee.
Okay, I guess. All right, so before we get into my topic, I want to spend a little bit of time understanding the audience, I guess. So how many people here are actually looking at using Linux in their network on the fabric side, on a switch or on a router of any kind? okay. It's about 2%. Well, and I was discounting. I was discounting the vendors. Is that what you? Yeah.
No, but ask the question is, what is a switch?
Yeah. So you're getting ahead of my script. No, I know. He's getting ahead of my questions. I have a plan here.
That's what you paid me for.
Yeah. No, that was for the next, that was for David's talk. All right, how many people, to Ronnie's point, how many people actually interact with the routers and switches, the thing that connect your virtual switches and your VMs and your NICs to each other? How many people do that for like a daily life? That's a very small percentage. Okay, so next question. For how many people have you ever had to deal with the issue that your network was doing something that you were not expecting, or you did something to the network that the network wasn't expecting, and it resulted in problems that you had to go sort out and understand and debug? Okay, so now the people who didn't put up their hands are sleeping. Because I assure you, you've had to deal with problems that came to the network if you're at this conference, right? Because at the end of the day, what it turns out to be is that a network is connecting a whole bunch of devices to each other. And your ability to be able to speak to the network is kind of important. And it should, and I assert the should, very strongly, be something that impacts your daily life if you're working on anything that has got a distributed system slant to it. So with that, let's talk a little bit about the things that I was told to talk about. So if you think about how, I'm going to do this because I can't see over that. If you think about where most people's sort of fabric components look and what it looks like, it sort of has this general shape, right? You have some kind of telemetry collection agents, you have some controller agents, things that talk to some orchestration tool. It could be something as simple as an Ansible or Puppet endpoint. It could be something very complicated where you're doing, sort of an SDN type infrastructure. You have people that are running routing protocols, things that are talking to each other, communicating across nodes and trying to figure out what the right thing to do is. Below that, typically you have a whole bunch of device-specific policy layers, right? You have things that do networking policy, it manages your link state, it does resource management of the kind that Matti was talking about. It manages all your system interfaces, like how does a device look to your application? Is it some random gibberish of special SDK calls that you have to make? Does it go through some kind of Unix interface? What is an error? Do you have a sockets communication channel, and so on and so forth? Below that, if you look at an operating system, that's typically where that line would be drawn. The operating system has to manage your actual device, right? I mean, there are DDR controllers in there, there's I2C devices, there's peripherals, block devices, all kinds of things to make the device work. And for the purpose of this conference, an equal-sized block called the networking stack. This is where TCP/IP is implemented. This is where congestion management is enforced. This is where ACLs are enforced. This is what you need to be able to talk to the rest of the world. And if you're talking in the context of a switch or a router, then underneath that you have your switching, routing, forwarding hardware. Typically it's an ASIC. If you are looking at state of the world today, it's typically a 64 by 100 or maybe 64 by 200 type device that can connect a whole bunch of devices to each other and do it at blazingly fast speeds. So if you think of this as the entirety of the box that is needed such that your network works, we can go forward and talk about what of these things are sort of well understood, what of these things need some effort, and so on and so forth. But before I go do that, I want to pause here for a second and see if there is anybody who wants to dispute a block, ask questions about what this block means, because even if you don't care, even if you're in the 98% majority of people who don't give a crap, it is something that you should understand, because this is something that will affect you if you're managing, operating, interacting with the network at some point. So I'll take a few seconds and see if anybody has any questions or wants to dispute a block. That's a no. All right. So everybody got it. Great. Moving along then. So what does Linux do today, right? And one of the things that I want to make sure, again, people understand is that actually in my former company, Cumulus, we spent a bunch of time making Linux complete from an enterprise routing switching stack perspective. And the grayed out points are the grayed out blocks are the ones that Linux does cover today, right? It's sort of inverted. Linux has a very good understanding of how to build agents because, Linux supports effectively a C library interface. And if you wrote an application or an agent that was a generic app that ran on a Linux box, it'll work on Linux running your network for obvious reasons. It understands how to do policy fairly well. Everybody here who's using networking in a server of some kind, or a laptop, or a standalone device of some kind, has some policy engine that they're using, whether it's interface management, whether it's route management, whatever the management thing that you're trying to do, you have a user space tool. And between IP route and its brethren, there's a lot of sophisticated interfaces that are available. There is no question that Linux knows how to manage low-level devices better than any other ecosystem out there, right? I mean, there's a reason why even Microsoft runs Linux on their internal infrastructure devices, because the coverage is unbeatable. So what are the pieces that aren't well supported natively in Linux? I mean, there's a lot of solutions. People have done interesting things. Cumulus has done one. OpenSwitch has done something similar. There's a bunch of solutions out there for how to manage the switching forwarding stack through a Linux interface. But natively in Linux, there is limited support. Mellanox actually is the only one that will allow you to say that at the bottom end of the network stack, I can plug in a driver set and I can go manage my switching forwarding stack. And the other place where Linux is lacking right now is exactly what we finished talking about, the resource manager piece. Like, how do you make it such that while there is very sophisticated support in Linux for understanding how a CPU works, how your RAM works, what peripheral devices do you have, how many blocks are you going to have, and so on and so forth, there isn't a sophisticated model for the networking side of it. So these are the pieces that aren't well understood, and these are the places where SwitchDev and all the work around SwitchDev has to focus on, such that the resultant solution from networking perspective is as good as anything else. So the parts that we are not going to talk about here are the parts in that red box. For people who want to understand that better, David has a talk tomorrow. Go listen to him. You'll learn a lot more. I'll skip it. What are we going to talk about? So what I'm going to talk about are two specific, three if somebody really wants to, two specific things that the industry has tried to do to sort of address a very particular problem, which is that layer. So I have solved all of the problems, let's say for the sake of argument. I know how the resource manager works because Matty and company have gone, and David and company have gone and written their code. The problem that still remains is, actually which came up even in the last talk, how do I have solutions like resource managers be generic? Because the absolute last thing you want to do is have your application need to know what hardware it's running on. Right? That's sort of been the foundational premise of an operating system. Otherwise, we would all be writing runtime applications that ran in real time talking to the low-level hardware. And every time somebody said, oh, can you run it on the next generation hardware, you have a heart attack. So you need abstraction. And this layer is the thing that is, at this point, very poorly understood. And there isn't a well-developed model. There are, again, examples of people who've done it. They all have some things that could be done better. So let's talk about the first one. How many people here know what SI stands for? And the Mellanox people cannot put their hands up, so they are out. I see, there's some games being played here. So not too many. So SI stands for Switch Abstraction Interface. It's actually incredibly popular. At this point, I think every switching ASIC vendor out there supports it. It was a Microsoft initiative, and the only user today is Microsoft's own operating system called Sonic. network operating system called Sonic. And the fundamental idea is that you solve this problem by specifying this interface, and every vendor wraps their SDK in this thing called a SI adapter driver that sort of provides a backend. But here's the problem with SI, right? And I don't want to go into details, and given the overall overwhelming interest, I'll stay at a very superficial level. But if people want to have side conversations, I'd be happy to entertain it, redirect it to the people who caused the problem in the first place, and so on and so forth. So SI fundamentally comes with no network model, which fundamentally means that that red box in the middle is sort of standing by itself. It doesn't know what's north of it and what's south of it. So the idea, therefore, is that SI has to be self-contained. It has to be self-annealing, self-protective, self-everything, right? It's the only thing in the universe that it can rely on. So there's no network model. SI has to sort of abstract everything, create a giant global union of every possible thing that every possible operating system can throw at it. And then it crosses that boundary, and then the adapter driver has to sort of take that global union and then refactor it into components that it can understand and is applicable to its underlying hardware. So while it's incredibly popular, while every OS supports it, the end solutions are actually quite divergent. And the end behavior is even more divergent because there is no network model that it has to answer to, right? So there is nothing, correctness is defined in the eye of the beholder, which creates a problem. Again, like I said, it's in the context of Sonic, it's very successful and it's very popular, but it does not become the answer to the thing that we're looking for. Another thing that has been gaining a lot of interest now is this P4 runtime or Stratum interface, which effectively says from a P4 program, we'll give you some generated RPC calls, effectively cut out all the middlemen. We don't need any of those guys. We'll have a controller agent that will take RPC calls from a person who knows everything about the network, and using these prefabricated interfaces, it's going to tell the... Is that music playing in my head? Time, yeah. This is... now somebody's going to come up. Actually, Roopa just told me it's the opposite. The stage is going to collapse and I'm going to get shut down. So anyway, so this thing actually takes everything else out of the picture and says, okay, what the hell, right? I don't need you to know anything. The network controller knows everything. Get out of the way. So these are the two competing solutions. This will also obviously result in a very broad generic solution. If you have a device that supports P4, you will get everything auto-generated. Your application will just make the same RPC calls using the same methods that you've always used, and the network device will sort of morph to handle your requirement. So if these are the options, how do we go solve this issue, right? This issue, like, sorry, that issue. How do you make it such that a vendor of a device can come in and say, and by the way, my talk was very switch focused, but this is true for NICs as well. How do I come in and say, here's my device, it does a bunch of cool shit, you don't have to worry about it, here's an interface that you can use. And how does the end consumer say, I have a bunch of really clever ideas, and I don't have to keep modifying it and tweaking it every time I change hardware for whatever reason. And so this layer is important, right? And we need to get this right. And I think if you look at competitive operating systems, let's call it Windows and VMware, one of the things that they've done well is come up with interfaces. Whether the interface is good or not, they've come up with interfaces, and people have been able to come in and say, here's my device, here's my driver, thank you. And we need to get to that point as a community, and this is not just a Linux thing, I think it's bigger than even Linux. So if these are the two horses in that race, I wanted to just sort of put my perspective, and we are only 3 minutes over time. I'm blaming Matty for that as well. But we also started late. It's all because of soccer. The score is still 1-1, right? Um, yeah. So these are the options, right? So Psi, one answer for Psi is assume a Linux networking model and build a test validation infrastructure around it. Number two, put it on a diet because Psi, as
Can
it
I say
stands.
something?
Sorry?
Is that your last slide? Or?
Yes.
Okay. I'll let the music play.
Oh, okay. Put it on a diet because as it stands, it'll never get consumed by the Linux kernel. It'll be a pretty hard sell. It needs a faster dispatch mechanism than the mechanism it has today. And it needs some resource management hooks. Hint, needs a network model. The alternative approach, the P4 runtime, one answer is extract the RPC dispatch routines and put it on the back end of switchdev, right? So basically keep the Linux stack, put the dispatch routines exactly in that red box, and call that the switchdev dispatch
I want to
function.
say there's other players in this space.
So,
There are other players in this space.
no, there are other options, you mean?
Yes.
Yeah, sure. And that's fine, but these are the things I wanted to talk about. You can come talk about yourself. And complete the loop. I mean, this is, by the way, even if this, what I'm saying is possible, there's a ecosystem problem here, right? Because P4 is something that's device specific. It needs to get in the kernel's driver infrastructure, and the update cycles might have problems. So that's all I have. Any questions, any thoughts, any non-Jamal comments? And there will be counters and TC in this model, so don't worry. All right, in that case, we'll stop here, yeah.
So Jamal,
Yeah. Sorry.
we have one more speaker, but I know we are eating into
Tom
Tom's
needs to
time
prepare.
right now.
He needs some time. So, how long?
So while he prepares, can
Yeah, sure.
he have 5 minutes? Tom, is that okay? Tom, do you want to stand for right now? Yeah, you just had less than 5 minutes, I guess.
I'll finish it in 2 minutes. All right. Quick updates from Barefoot Networks. So I'll fly through the slides. Okay, let's see. So simply put, programmability is brought to high performance networking. So traditionally, switches have been fixed function. Now they're programmable. P4 is the programming language for programming, fully programmable switch ASICs. We are one of the manufacturers. And if you look at the performance, the highest throughput device we have is 6.5 terabits per second. It's currently the world's fastest and fully programmable Ethernet switch ASIC. So actually, thanks to Srijit and Matty, I think we are talking about the switch space. This is the fabric area, not the hosts. The slides look interesting. Okay, so the architecture has become a little fat. It was much leaner. Anyway, the idea here is the switch has a programmable parser and a deparser at the end, and then a bunch of match action units. So the switch doesn't know anything about packet processing until you write a P4 program and tell it what to do. So can create all kinds of interesting possibilities. So somebody asked, what are the types of applications people are using these kinds of devices for? I mean, in addition to like your standard routing and switching, which you can adjust to achieve more scale because the resources in the silicon are programmatically assigned to whatever protocol or feature you want, people are also doing things like real-time telemetry. In-band network telemetry is one. In-band OAM, IOAM is another. People are also doing things like layer 4 load balancing, trying to offload some of the layer 4 load balancing functions onto the switch instead of using an appliance or a server. Of course, security, DDoS mitigation. You can do things like you can challenge TCP connections on the switch itself without going to another device. DNS caching. You can actually respond to DNS queries in the switch itself. People are offloading 5G gateway functionalities onto the switch device. We're also seeing people use it for accelerating machine learning workloads, you name it. I mean, the switch can do what you want it to do. So as long as it's getting packets and you can extract the headers and decide what to do, it can do it. So now this is kind of capturing some of the points that Srijit was talking about, as well as Matty before. So I'm showing, we have the programmable device underneath, and there's multiple paths into it. So SI is the same thing, the switch abstraction interface. There is a NOS that uses SI. It's currently Sonic. The NOS-B is, these are like OEM NOSes, which can use program-dependent APIs generated from P4 program using the compiler. The NOS-X is kind of like the controller that Srijit was mentioning that uses P4 runtime, so it can directly go to the PEI API. And earlier this morning, Antonin actually talked about how do we make use of SwitchDev as well as TC and XDP for controlling programmable hardware. SwitchDev would be used for standard apps, standard protocols, and then TC XDP for custom apps or custom protocols. So this is the lay of the land. I mean, programmable devices can do whatever you want, but I think it's good to understand how to leverage Linux and the utilities in Linux, and then take advantage of this Linux networking ecosystem on top of programmable switch hardware. So that's all I had. Thanks.
Thank you, everyone.
I got it through TSA. I'm good.